am proud to present you the famous, the one and only, Dr. Aleksandar Kondinski.
Thank you. Good morning, everyone. I would like to apologize first myself for the voice. I got a bad throat ache, a good throat ache for a bad voice. So if it sounds a little bit shaky and I cough, I'm very sorry. Today, we heard in the morning that chemistry can be green, chemistry can be also magical. What I'm going to talk about is chemistry when chemistry is beautiful. And why is that? Because most beautiful people always work in chemistry. And this is not really something I make up, it's a fact. Yeah? Look around, think about it. So, but it's not only beautiful, right? You need to be beautiful, but also stable and functional. Bringing these things together, and this is sometimes not very easy, yeah? So, who is this Vitruvius? When you think about Vitruvius, often people think about Da Vinci, and Da Vinci had the idea of the Vitruvian man, or maybe Vitruvian woman, yeah? So, but it comes much earlier than that. So, over 2,000 years ago, there was a Roman architect who was very, very fascinated with proportions. So he looked at the proportions in the human body and he thought that this is actually the perfect way to translate proportions also to large structures and to make them beautiful. And this person is Vitruvius, Vitruvius Pollio, and actually he says that basically a good architect gives attention to the proportion to the highest detail. And think about chemists. Chemists are also keeping very good attention to proportions. And if you look, for example, we can Richter, Proust, Dalton, Lavoisier, they actually found that chemistry based on proportions. But chemistry is not only proportions. Chemistry is also architecture. And we have to ask Vitruvius, what is a good architecture? And Vitruvius basically says the three principles. It has to be stable, it has to be functional, and it has to be beautiful. Firmitas, utilitas, venustas. And where do we see this? In chemistry, we see this very often. Think about the buckyballs, the carbon-60. We have them here, simple models. Or the capillaries, or the DNA. These are all beautiful molecules. They are highly symmetrical, and they have function, and they are really stable. Think about the viruses. They are killing machines. This is the capsid, it's highly symmetrical, it's stable, and inside you have actually DNA material which can be harmful. But if you pursue chemistry, you will see that all these functionalities are different, and you will study this in the different classes: physical chemistry, inorganic chemistry, biochemistry, whatever. But you have to look at the big picture. And big picture is that they are made of building blocks. So the building blocks can have functionality. But the point is about the building blocks is how they integrate together. And when they integrate together, they affect the stability. So think about building blocks, something very simple. Something which are called these Steckblumen. These are very cheap materials you can buy in a supermarket in Germany. If you actually properly assemble them, you can get very beautiful structures, highly symmetrical structures, but you need to program them correctly. And if you change from 8-fold, what we have here, to 6-fold, you can get these beautiful structures here, plus the ones that we have here. And you can have a lot of them. But very often, when you build these things, you realize you are having problems to close structure. And this has to come with strain. And who to speak to strain, if not to Adolf von Baer? He came up, actually, the first type of building blocks he was looking at is a CH2, which can connect in two sides. And of course, you know, if I connect it further, I will get a zigzag chain. Very easy. But now the idea is, what if we can make a cycle out of it? And when you do a cycle, you will see that you can have many cycles here. But the angle here is about 109 degrees, and you will see that this is not really, 90 degrees does not really fit. And this is where you will get high energies. This is unstable molecule. And Vitruvius is all about stability. So your building blocks, how you integrate, it's very important. you will not always get what you want. So you have to know what you are doing. Now comes the other one. You can have only one CH, which can connect to 3 other. How we can connect them? Look at also beautiful things, platonic solids. Not all of them, only some of them. Here you can see that you can connect them with 3 other sides. And people have built, in this way, tetrahedron, cubane, and dodecahedron. The difference is that the angles are causing too much strain for these 2 structures. But here they fit well. They are very, they're not easily to be made, but actually they're really stable afterwards. So the point is that we want to build big. Yeah? We don't want to build small, we have to also build big. So building big, you can think about what if you use only single carbon. And when you use a single carbon, of course, and this is sp2, to be planar, to be trigonal, you can get something like graphite, and if you pull one strain, you'll get something like graphit. I have it here. So it's just a normal sheet. Now the point is that when you want to make a structure for this, you have to bend it. But then you get a strain. You have to pay some energy price. And this is how you push the building block out. You lose a little with stability, but you get a new functionality. So this is what happens often. Some of these nanotubes, like the big brother here, they can be also semiconducting. Some can be also conducting, depending how you connect them. These guys here, the fullerenes, you can store electrons there. So why not? Well, actually, I'm looking at my favorite building blocks are inorganic, similar, but they can be also programmed. And the way they can be programmed, they can give a lot of possibilities. But the idea is to look which of these possibilities make sense, and which of these we can isolate, which ones we do not isolate in solution. But to understand this, we also have to look at their profiles, at their strain profiles, and we do this using, of course, computational chemistry. So, why is that important? We are using this on molecular metal oxides. And metal oxides are the most common materials on the Earth's crust. So harnessing them, we open the way to new technologies. For example, quantum computing, batteries, memory devices, homogeneous catalysis, name. But the way how you program, it's very important, and all depends on the building blocks. So we have been using this, we have been successful to find out how basically to understand how matter works, how stability works. We have been also looking how we can trigger some of this to get catalytic activity, which is very useful. Or finally, even maybe design some functional advanced materials. So from most of you, who would like to pursue chemistry, I would just want to say, chemistry is the art of building. But the way how you can go, the style to build, I believe it's a Vitruvian. Keep in mind, you will always want to build molecules which are stable, functional, they can be highly symmetrical, or, for example, you can devise some elegant way to make this understandable way. The other one is that you cannot use the same building block to build whatever you want. The building blocks do have some strain effects, and you have to understand how this works. You can do it by hands, by models, or you can use computational methods. And the last one is that, as early as possible, develop spatial reasonings. And this is not always straightforward. Building models like this, based on Steckgluon, on these interlocking disks, are useful, but of course there are also other methods as well. With this, I would like to close, to thank all of you for your attention, and stay beautiful, yeah? Thanks.